more exciting. Good. I like that. Okay, good. That makes it better. Okay, because we start with the position vector. I'm going to switch back to that other type of marker. This guy is a little hard to erase. Get more exercise than I want today. Okay. So we have this thing given to us as 2/3 t cubed minus 3/2 t squared I plus t to the 4th over 12 j meters. So cranking the derivatives, we've got 2t squared minus 3t I on the velocity plus t cubed over 3 j hat, and this is going to be meters per second now, and we hit the derivative on that and we end up with 4t minus 3 I plus t squared j meters per second squared. Straight math so far. Drop in, why don't we do it at 2 seconds? At t equals 2 seconds, r at 2 vector is going to be 2 going in here is 16/3 minus 6 I plus 16 over 12 is 4/3. Is that right? Excuse me?
Unless you want to explore something else in the problem, that value shouldn't be necessary. You just work with the velocity and acceleration.
Yeah, I do want to explore something else with it, so that's why I'm doing it. And so r at 2 is, that's 18/3, taken away from 16/3 is minus 2/3 I plus 4/3 j. Its physical location, that's the physical location at 2 seconds. Off to the left a little bit and up 1 1/3 at 2 seconds. The velocity at that same point in time then, with the 2 dropped in here, is 8 less 6 is 2. 2 meters per second to the right. And at 2 seconds, 8/3 j. Meters per second. The acceleration at that same moment of time is 8 less 3 is 5 meters per second squared to the right. That's more than half a g, isn't it? 5 meters per second squared to the right is more than half a g acceleration to the right at this instant. And the j term is, at 2 seconds, is 4 j, a little less than half a g. A little less than half a g, because we know it's 9.81. Try to always, whenever you see an acceleration value, try to think of the physics of it, the physical sensation. Okay. Now, that would answer the velocity and acceleration values, but that isn't the question that was asked. They want to know the angle between this velocity value and that acceleration value. So why don't you talk to your neighbor for a second? Actually, If your neighbor's real talkative, let them be quiet. And if you're the quiet, silent majority, you speak up, okay? And offer a suggestion on how you might determine the angle between these two vectors at this instant. Talk to a neighbor, pair up with somebody near you.
No, I mean, by all means. No, I am not fucking away from that. I haven't taken the inverse cosine yet. The problem is, I really feel like this should be somewhere between 1 and 2. Now, I can still take the inverse cosine like this, and it'll give me something. But I shouldn't try
this angle, subtract that.
exactly what I have. Wait, I have 64 over in.
When you did this over this times this, it might have tried to multiply this.
No. I did this all one step at a time. I mean, like, I could do it all at once on the calculator because I'm a magician with the TI-36. So,
It's like
no order of operations. Oh no. 25 plus 16 is 41. Okay, that's that. Okay.
That's not this one.
4 times 9 plus 64 equals that.
109.
So it's okay. So it's not 4/3.
If the velocity is the third direction.
So this is 6.2.
Okay, this is the kind of little graphics that I'd like you to include in your work when you're doing a problem such as this. If you look at this velocity at 2 seconds, you'll notice that here's a little sketch of it with its orientation. And there's some internal angle right there between the x and the y components, or between the actual velocity vector and the x-axis. Similarly on the acceleration, a 5:4 ratio, so there's an angle in there. The question asked, what's the angle between the velocity and the acceleration, so we want the difference in these angles. And you'd use what trig function to determine each angle? Inverse tangent, right? Opposite over adjacent, inverse tan of that. Okay? So we go, what we're looking for is the angle at 2 seconds is going to be equal to the theta V2 reading minus the theta A2 reading. So I write this math out. I've got that little sketch right next to it, so you could look back at this 5 years from now and make some sense out of it. And you might even want to write down the angle between is, comma, here it is, and you just crank the inverse tangents there. Inverse tangent of 8/3 divided by 2 minus the inverse tangent of 4/5.
Do all tangents combine in any way? Or we start with that?
I would not choose that. No, I would not try to think of it.
Combine in some way, we might be able to stick
Yes.
our original V and
Yeah.
A expression in there and make some math out of it.
Right, this is some physical angle, isn't it? Isn't this a physical angle? Yeah, this is a physical angle. So there might be occasionally in trig, there are things where things through theorems and so forth can combine. I don't think I'd do it in this case. Now, if you crank this out on your calculator, did anybody do that, degree measure? Yeah, what'd you get?
Yeah, that's about 14 and a
Ian
half.
got it right, 14.47. You can see it up there in the book. Okay, so this angle should be at 2 seconds, should be approximately 14.47 degrees between those two vectors.
Yeah, we do.
Yeah,
Certainly should be able to, yes.
that's what we just did. We got
Good, excellent. As a
Actually,
matter of fact,
that ought to be how they combine.
yeah, and what I'd like to do is actually take a moment to go through that with you, because that's something you want to make sure you refresh your memory on is dot products, because we will use those quite a bit in the course, okay? Now, I just kind of brute forced it through here, just crank derivatives, drop some numbers in, and then look at the physical situation and figured it out that way. So coming at it like Moshe Rubinstein, I mentioned last week, would do it. He'd come at it a different way, hit it with a dot product, and then he'd probably come up with some other way that I've never thought of to do it as well. Okay. So let's go ahead and do that with the dot product. So we'll step back over here. We have expressions for both the velocity and the acceleration. And so we have two vectors. You can see from the little sketches there that our velocity vector is looking something like this at 2 seconds, and the acceleration's not as steep. And of course, there are totally different units associated. They're totally different units. And which one looks like it's bigger? The acceleration as far as the scaling goes, yeah, and lesser angle. So I don't want to make it that long. Let's say it looks like this. Okay, so there's those two vectors sitting there. We're looking for this angle between them. And so what you've learned from your vector calculus experience is that the dot product of two vectors, v at 2 dotted with the acceleration at 2 seconds, is equal to the magnitude of each vector. Notice no arrowhead. The product of the magnitudes times the cosine of the angle that exists between the two vectors. So we can do the dot product, and remember what the dot product is. It's the product of the scalar terms. So the product of the 2 and the 5, and we add to that the product of the j terms, 8/3 and 4. There's our dot product, which is 10 plus 32/3, which is 62/3 in value. And that's equal to the magnitude, the product of the magnitudes of each vector. And so we're going to have a magnitude here of the square root of 2 squared plus 8/3 squared. Inside the radical is a 4 plus 64/9, which is 36/9. And 64 is 100/9. Oh, we like that. The radical of 100/9 is 10/3. So we have that one. And the acceleration term, its magnitude, is the square root of 25 plus 16. 5 squared plus 4 squared is 41. Radical 41 times the cosine of the angle between the two. So if we multiply both sides of the equation by 3, we get rid of that. We end up kicking this over to the other side, and so it looks like we get 6.2 divided by radical 41 is equal to the cosine of theta. I'll tell you, stop me if I make a mistake. I make mistakes all the time. Sometimes I do it intentionally. More often than not, I don't do it intentionally. Okay? So we want the inverse cosine of 6.2 over rad 41, and that better come out in degree measure.
Yep, 14.47.
14.47 degrees. So we're feeling pretty good about that. Okay. Nice suggestion to hit it with a dot product there. Okay. What I wanted to also do with you was to take that same problem in parametric mode and just have you know how to do this with using your calculator, not for finding the angle between the two vectors, although we could play a game and figure that out, but it would take more time than it did to do the hand calculation, but to actually see what the flight path looks like. You can use your graphing calculator for two-dimensional problems, quite sophisticated two-dimensional problems. So what I would suggest you do is take your graphing calculator, and I need to come out a little bit here probably. There we go. And go into, you can just take notes on this if you wish and jot some numbers down. Parametric mode. And we'll enter this X profile. Which is 2/3 of t cubed, and subtracting from that 1.5 t squared. And then the y profile is t to the 4th power divided by 12. And then I took the time to play with this a little ahead of class just to save a little time here in class. And so if I set my viewing window, it gives me the control over the time we wish to let pass. So if I let it go from 0 to 3.1 seconds and let the step be every 100th of a second, and then set up a viewing window that will fit this flight path, -2 to 8. You can just jot these numbers down in a list and then go home and duplicate this if you wish. -5 to 10 and scaling on 2. Okay, now here comes the pretty picture. I'll pause it once it gets moving. Come on, where is it? Oh, there it goes. Boy, that's slow. Okay, I paused it by hitting the Enter key on the calculator. Yeah, I'll just let it keep rolling. Notice it looks like it's speeding up, doesn't it?
Yeah.
When you're in parametric mode, you have a time step there, and that's pulsing. The calculator does those calculations in equal increments of time. Okay? And it takes us just as long to do one calculation as it will the next calculation, okay? So when you're in parametric mode, you can actually have a sense of the motion, including its speed. If you see it starting to move faster, that means it's been speeding up. Okay. So there it is. There's its flight path. Now, if you look at it at, say, 1/10 of a second, whoops, let me turn trace on. If I go to t equals 1/10, let's say 1/2 a second, because we didn't see much action there. You can see where it is here physically. And so it starts at the origin. You can look at your equations and see that it begins at the origin, and it sweeps out here, rising very, very slowly as time passes, and sweeps out here, makes a hard curve, and then sweeps on up, and then heads on out almost in a linear fashion. Almost in a linear fashion. So then at 2 seconds, here it is at its position. At 2 seconds, you can see it's at X position of 2/3 and a Y position of 4/3. 2/3 and 4/3, which jives with what is up here on the board. Okay? So there's its physical position. Its velocity is what direction there? At that spot? Tangent to that path, isn't it? Tangent to the path right there is its velocity, and then its acceleration happens to be pointing which way? This is here we are, tangent to the path at that instant, shown on the graph, and then here it is, and you can see that the acceleration is slightly below this angle, isn't it? Isn't this a greater angle than that one? You can look at the ratios there. Yeah, because this is greater than this, right? So this is greater than 45 degrees, and that's obviously less than 45. Notice, what's the curvature at that instant? It's concave down, isn't it? See, in this acceleration term here, you can see that there is a part of that acceleration that is tangent to the path, and there's another part of it that happens to be perpendicular and inward, which allows it's actually following right at that instant, even though it looks pretty straight up there on the calculator screen, it's actually sweeping concave down slightly there.